Good evening, everyone. Hope you all are doing well. So today we're going to be discussing chapter 6. We also have a lab. So next week is spring break. So yeah, you get another lab assignment before spring break. I know, I know. That I'm just such a great professor to give you guys 3 labs and they're all due in less than 3 weeks. It's okay though. I know you guys have it in you. You'll get it done. Yes, sir, Lawson.
For the bridge lab,
Hmm.
the what's it called? The simulation part of it, do we have to like print out for each like design that we had to do and then put that in our
Uh-huh.
book?
So you needed to you only need one design, but if you had like a few concepts, you could put
Mhm.
that in your lab notebook, yes. But your report should only be on
Okay.
one lab or one bridge rather.
Okay.
And that goes for your boat. Go ahead.
So like we print out like our like main design and then put that in our notebook, and then like do we just take pictures of our notebook and submit that into the bridge lab notebook part?
Oh, you talking about the assignment?
Yes, sir.
Yeah, yeah. You can scan in your make scan copies of your notebook and upload it to your lab notebook assignment.
Okay, and then for the max tension and max compression, is that on the simulation part too?
Yeah, you can use it from your simulation, but for the most part is whatever weight you apply to your bridge. That's more or less where you're going to get it from.
So
But
like the
if you use the simulation for say you used uh, a certain amount of weights on
hmm
your bridge, and then you will put that into the simulator,
Yes,
and then
sir.
that should give you a tension or compression.
Okay. Okay, thank you.
Oh yeah, no problem. Yes, Cassandra.
Also, there's a part in the lab where we need to put the compression for the 4 type of bridge. We need to do that or just for one?
Yeah, just do it for one.
Just for one? All right.
Hmm.
Thank you.
Oh yeah. Anyone else? All right. So remember, guys, that lab report is due, I believe, tomorrow. I have to double check, but I think it's due tomorrow. If I made it due Friday, then I'm gonna make it due tomorrow. No, I'm just playing. I'm just kidding. I'm just kidding. If I set it to do the due date to Friday, then it'll be due Friday. Uh, but yeah, I think everybody did well on their test for the most part. That if you did it, if you didn't do it, then obviously you didn't do well. But for the most part, everybody did really well on the exam. So kudos to you all for being prepared. Um, yes. So back to chapter 6. Chapter 6, going to be discussing the fundamental dimensions and units. This is an interesting chapter. It's really cool, real simple chapter. It won't take us long to go through a lot of it. Um, so then after we're done, then we'll go over the viscosity lab, and then I'll either turn you guys loose or I could set you up. It's not very many of you here, so I know a lot of you are not going to have partners. So if you all want to get set up, for those of you that have everybody here for their group, I can break you out into groups, or you can all just disperse as you want and chat about this new lab. So, all right. So I got a little discussion starter. It's kind of long. I'm going to read it, uh, but just to get us ready for this lecture. I like to wake up your brains and your minds, what have you. So let's jump into it. Chapter 6. If you have the 6th edition, it's on page 159 if you want to follow along. And it reads, fundamental dimensions play important roles in our everyday lives. Throughout history, human beings have realized that we need only a few physical dimensions or quantities to describe our surroundings and daily events. For example, we need a length dimension to describe how tall, how long or how wide something is or how far, right? We also use 2 or more length dimensions to calculate and describe the area and volume of something. When you're cooking, right? That's where you're going to use volume anyway. Time is another physical dimension that we need to answer questions such as, how old are you? Yeah, that's a big one, right? Nobody wants to say how old they are. We want to say how young we are. When are you coming over? Or when is the next test? That's a big one. It's coming up, actually, next week. No, I'm just kidding. It's not. Based on what we know about our world, we use 7 fundamental dimensions to correctly express ourselves and our surroundings today. They are length, mass, time, temperature, electric current, amount of substance, and luminous intensity. Luminous intensity, if you all don't know, that's light, intensity of light. But anyways, the other important uh, concept that we have learned is that not only do we need to define these physical dimensions to describe our surroundings, but we also need some way to scale or divide them into units. For example, dimension time can be divided into both small and large portions, such as seconds, minutes, hours, days, months, years, and so on. Take a few minutes to think about the previously mentioned dimensions. That keys a tongue twister. Sound like I said the same thing, but I didn't. Previously mentioned dimensions, and consider how frequently you use them in your daily life activities during the past week or today, right? Did you use the length dimension? Yes, no, maybe. Or its related quantities such as area or volume. If you all cook, I'm sure you use volume. I mean, that is if you use a measuring cup. Some of us probably don't need it. It's just like, I know I need so many, da 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 da. You eyeball it, in other words. I'm being silly. Did you use the time dimension? Of course, we all use the time dimension. Is my screen frozen? No, it isn't. I'm not moving. I have my slide on the same page. I didn't turn it. I'm reading from the book. So page 159 if you have the 6th edition. I'm not sure what page it is in the 5th. So I'm asking you all these questions, right? And so you can feel free to answer, any of you or just one of you. It doesn't matter. Did you use the length dimension? Did you use volume or area? What about the temperature dimension? Was it really cold? Was it really hot in your place and you changed the temperature? Did you tell someone else that you may be living with to change it? How did you use these dimensions? Anybody? Nobody? Somebody? One body? It, it makes it. I use the link all the time because I work in a shop. Cool, cool. What kind of shop do you work in, Mason?
I'm a bicycle mechanic.
Oh, nice. So you are fixing bikes or
Yeah, I'm actually a master bicycle technician. Yeah, I fix them, overhaul and build them.
nice. So do y'all sell bikes there too?
We're limited right now, but yes, we do.
Okay, since I'm your professor, I can come by and get a discount.
Yeah, yeah.
I'm just kidding.
I get extra credit though.
No, that's cool. That's okay, cool, cool. So yeah, you use temperature a lot. You probably use more than that. Yeah, I mean because you're using wrenches, so you're gonna be using sizes, different size wrenches. So you're using length a lot, right?
Yeah,
Yes,
yeah,
no,
quite a bit. Yeah,
right,
especially for
right.
like building wheels and stuff too.
Absolutely, absolutely. So length is probably one of the major ones because if you're driving, you're gonna look up distance and then time, right? Distance and time, and then maybe temperature, because you're gonna be changing the thermostat either at your place or at your job, right? So that's why units are important, right? Because it gives you the measurement of something. And what type of units are also important. So today we're going to talk about that. We'll talk about units of measure. We're going to talk about different types of units of measure, the system of units. Got imperial, you got SI, and here in the US we use imperial. And I always tell my classes, I think the United States is probably the only country that mainly uses imperial. Everybody else uses SI, right? Excuse me, millimeters, um, meters, things like that. We use feet, yards, things like that. Inches, that's all imperial. Because you notice when it comes to meters, it's meters, millimeter, centimeter, and so on and so forth. But it's all a meter, right? That's the unit of measure. And then you have milli, center, or what have you, is to what degree of that meter it is, how big or small that meter is, in other words. But anywho, I named all of these different fundamentals earlier, but I'll just go back through them. You got units, you got length, time, mass, force, you got temperature, electric current, and energy and power. All right. So let's go to units. A unit is used to measure physical dimensions. So we was just talking about bicycles. When you're thinking about putting a bicycle build together, you got various types of nuts that goes on to certain screws or what have you when you're assembling a wheel or what have you onto the bicycle frame in order for you to pedal, or even your pedals. You're gonna have certain thread size when you screw in a pedal in, right? And all of that is dealing with length, right? Because there's a certain diameter that the pedal hole is, or the female portion of the pedal, and then you got a male portion of the pedal with the crank, I believe it's called, what have you. And I'm not an expert on bikes, but just giving you a visual, so to speak, of what that length is when you're looking at the measurement of it. So you're looking at that diameter, and you're either going to be measuring that diameter in units of inches or millimeters. And so if you're working in tighten wrenches, hey, you got to know different sizes of what size wrench to tighten that size screw or nut or what have you. Now, systems of units. Again, I spoke about the SI units. I spoke about imperial. Here they call it U.S. customary units, which is the same thing as imperial. But then you also have the British gravitational system of units. So for the most part, what I want to really focus on is in units. And remember, I talked to you about this from an engineering standpoint. You want to look at unit conversions, right? Like some people are going to be here in the U.S. Let's say some people will use imperial, but then say over in a different country like Canada. Now, some parts of Canada they use imperial, but they use imperial and also SI. So say you were going to go to Canada or you were going to go to Europe more or less, they use solely SI. Now you're going to have to convert whatever you're doing from the US when you go to Europe. You're going to have to make a conversion. And so when you're doing an engineering problem, you may have a mixture of units. You may have imperial and also SI units. So what you're going to be doing is converting from SI to imperial or imperial to SI. That's why units are important. And when you're looking at a problem, in which, if you remember when we were going through the Excel portion or Excel chapter 14, there was that time where you would have imperial and then you would have SI units all in one problem. That's why you have to watch your units. All right. That's why units are important. Because if you're trying to solve a problem with inches and meters, you're not going to come out. You're not going to come out right. So you think about building a car. You got certain portions in inches and others in meters. And that conversion is like a 1 inch. It doesn't equal 1 meter. And so, yeah, units are very important. I know a lot of you that are working in shops and things like that, you know that. But if you never touched a wrench, you probably wouldn't know. Hopefully, all of you all touched a wrench. And this is not important. Well, it's important, but it's not like, I'm not going to go over it, right? Because you know the unit of measure for mass. Length is meter, mass, kilogram. But I'm not going to go through all of those. Ampere is current. Kelvin, temperature. I want to get to, okay, so force pound. And the BG, British gravitation, and imperial, we both use pound. But you see more slug in the British gravitation units. They use a lot of slug. Even with their, I think in their currency, I'm not sure. I don't know if they use slug or not, but I know they use pound. But anyways, but for their mass, they use slug. We don't use slug. Trying to get to an example. Let me go over here. Because we're going to be working some nice examples. And the first one I want to view is temperature. There we go. All right. So converting temperature. All right. We're in SI in Europe, they're going to use a lot of Celsius. Here in the US, we're going to use Fahrenheit. And so the conversion for Fahrenheit. So if you have Celsius, you're trying to convert from Celsius or Fahrenheit to Celsius, you're going to go 5/9 times the Fahrenheit, whatever that temperature is in Fahrenheit, minus 32 degrees Fahrenheit. All right. Or minus 32. And then they worked out the problem, and then they got it converted to 26.7 degrees Celsius. So a rule of thumb, right? If you're in a different country and you're trying to figure out, this is just a rule of thumb. You can do multiply times 2 or divide it by 2, because 5/9 is roughly 2, not quite 2, but roughly 2. So it'll give you a ballpark of what the temperature would be from Fahrenheit or Celsius. So if you're converting to Celsius, then 5/9, that's roughly 1/2. If you're converting from Fahrenheit to Celsius, you just divide it by 2, right? Subtract 32, then divide by 2. And then if you're going to go from Celsius to Fahrenheit, you multiply by 2. So let's find an example that we can work together so I can get to my handy dandy whiteboard. Well, let's just do a temperature one. So y'all have that memorized, right? All right, good. So let's go to my whiteboard. Get you guys talking. Y'all are real quiet. Y'all about to go to sleep. I know a lot of y'all probably just got off work. So, let's wake up. All right, what's the current temperature? Somebody, anybody. What is your current temperature?
$68, $69.
All right, so we're gonna go 65 degrees Fahrenheit. And we want to convert. We're gonna convert that to all right, what do we need to do to convert that to degrees Celsius?
You need to do the 5/9.
All right, so 5/9.
Is it the same way? Because like in chemistry, I learned it as the 1.8 to the cell to the the Fahrenheit minus 32 over 1.8.
Okay, so I go 5/9, 65
Mm-hmm.
minus 32,
Mm-hmm.
and that equals. So I multiply 5/9 times 65 and subtract 32, or what do I do? Oh, like they left you by yourself, Austin. You're on your own.
You subtract first.
All right, so you
There's
subtract
supposed to
first.
be parentheses there. So subtract first and then multiply.
All right, so you're saying I should put some parentheses there. So then I have 5/9 times 33, and that equals what? Tough crowd today. Hmm. Nobody wants to. Nobody wants to do the math. I know my scribble scribe was probably distracting. So just like I said, I mean, my house is always moving. Or my apartment, it's always moving over here. So it's like an earthquake here. 18.3. Cool. Thanks. Cool. Cool. Thanks. Oh, that's an 8. That is an 8. Wait. We're gonna get that fixed. All right, so that was easy, right? 18.3 degrees Celsius. So what if I want to convert that to Kelvin?
Lawson lost signal in his house, by the way.
Okay. All right. Thank you, Mason. What if I wanted to convert this to Kelvin? What do I need to do? Then you add 272 degrees. Thanks, Phyllis. And that gives us what? So that'll be T Kelvin equal to 273 plus 18.3, and that equals 291. All right, that's easy as well. All right. Sorry. Just trying to see if little JoJo, my little Yorkie, is going to leave out of the room, and I guess he's going to stay. So moving right along. So converting length, and it's fairly easy. So what if we wanted to convert gravitational force? How will we go about doing that? So you're gonna have to do a little bit of research on that. I'm not gonna tell you. I'm gonna wait for you guys to tell me. So what we want to do is force. Force in imperial is pounds force. Now in SI units, a force is a newton. So what do we need to do to convert 1 pound's force to 1 kilonewton, or to 1 newton rather? Oh, it's right there. Ah, man, never mind. That's too easy. You ain't have to look up anything. It's right there in the slide. All right, never mind. That's the easy one. Figure out another one. So if you can't tell, all we're going to be doing is doing unit conversions. So let's see if I can find. Oh, all right. Let's do one more, and then we're going to go to significant digits, because people get this wrong quite a bit. But I want to work in a problem out of the book. It's one of the harder ones. It's one of your homework problems. Let me find it. Let me go to your homework. That'll be easier. All right. Chapter 6. Yeah, it might be 621. Yep, 621. All right, somebody want to read that for me? I feel like I'm in class by myself. Anybody want to read problem 21? It's in chapter 6, page 196 if you have the 6th edition.
You say 21?
Yes.
So 6.20. Okay. A cantilever beam shown in the accompanying figure is commonly used to support a load acting on a balcony. The deflection of the center line of the beam is given by the equation. Do you want me to read the equation?
No.
Okay.
Nope. You can skip all of the nomenclature and you can add this. What are we looking for?
It says, what is the appropriate unit for W, which is distributed load, if the preceding equation is to be homogeneous in units? Show all steps of your work.
All right, cool. So what we're doing is solving for W. All right, and so let me just give you one little correction. Let me find it. It's like they made this edition, right? The 6th edition and the 5th edition, and there was an error in both, and I never changed it in my book. I'm gonna change it today though, once I figure out which one it is. So in this equation, they're showing x cubed. So they're showing negative wx cubed. It should be negative wx squared. All right. So if you all make a note of that. Remember, this is a homework problem. So I'm going to stop and go to my handy dandy. It cut out. Oh, can you hear me now? All right, good deal. I'm going to write it down. So where it shows y is equal to negative wx cubed in your book, it should actually be negative wx squared. All right, but I'm going to write it. I'm going to write it down on my handy dandy whiteboard. All right, so y, I know you can't see me typing, but it's okay. You'll see it once I'm done, is equal to negative wx squared divided by 24 e I. And that's all multiplied by x squared minus 4lx plus 6l squared. All right, do y'all see that? All right, so in your book, you're gonna see that it says negative wx cubed, but it should be negative wx squared. All right. Now that you see that, what we're solving for is w. So w equals question mark. Oh, so in your book it says negative wx squared, not x cubed? Because in my book it says negative wx cubed. But in either case, it should be negative wx squared. So now we need to solve for w. So before we do that, we need to check the units of some things. All right. And I'm going to write with my pencil so you guys can see everything. So what it is, W is the load. All right. So what are the units for the load? Well, you know what? Let's skip that one. What about Y? What are the units for Y? Units.
Is in meters.
Meters. All right. Units for modulus of elasticity.
Newton meters squared.
Meters. Moment of inertia. Or moment of area. I.
Meters, I guess to the fourth, is that like?
Meters to the fourth. I'll move that. All right, so meters to the fourth. And then L and X are just meters, correct?
Yeah.
All right, so what do we need to do? We need to get W by itself. So what do we need to do? I'm just gonna follow you guys. What do I need to get W? What do I need to get W on one side and everything else on the other side? Wow, it's a tough crowd tonight.
Multiply every or divide everything in the parentheses over.
Divide everything over.
Everything in the parentheses, right?
So you got
multiply.
both. I put both in parentheses. So if I
Oh,
write it
I was
out,
looking at the formula, sorry.
no, it's fine. So if I write it out, negative W.
I would divide the x to the x squared.
I was trying to type it so it would look prettier. And that's times x to the negative 4 minus Lx plus 6L squared. And you're saying divide all of this by
Yeah.
both sides?
Yes.
All right, so we'll do that. So we got y over x to the negative 4th minus Lx plus 6L squared. And that all equals negative W x squared over 24 E I. All right, now what?
Why is it x to the power of -4?
Was that not it from the book? It was x squared.
I see x squared
On mine says
minus
x squared minus 4 Lx.
All right, see that's why you guys got to talk to me. I'm just writing. Is it negative? No.
Mine just says x squared minus 4 Lx plus 6L squared.
All right, thank you. Appreciate it. And see who's gonna have this all messed up. All right, good deal. Is that? I mean, I know it looks horrible, but is it reasonable? Like, is it correct? Now, y over x squared minus Lx plus 6L squared is equal to negative W x squared over 24 EI. Is that correct?
Yeah.
All right, what do we do now? So when I was
I
in
think mine's
school,
different because mine says x squared
go
minus
ahead.
4 in front of the Lx. It says it's a 4 in front of the Lx.
See,
Yeah, it says that in mine too.
all right, there you go. Good deal. Now we're helping. Now y'all are helping me out. All right. So is it right now? Is it correct? X
Yeah.
squared minus 4LX plus
Yes.
6L squared All of that's equal to negative WX squared over 24EI. All right, what do we do now? Because we're trying to get W, we're solving for W.
Yeah, I was
Multiply both sides by 24EI. All right, cool. So that'll get rid of that. And 24EI will be there. And I guess if you divide by negative x squared, both sides by negative x squared, all right. So when I was in school, what we used to call that was cross multiply. That's what we call that. Called cross multiply. So we would have done that basically here, cross multiply here, and then divide it to get your W by itself. But either way, it works. I'm not sure if you guys are familiar with cross multiply, but it's okay. We have it isolated now. W is equal to 24 E I Y, and that's all over negative x squared times x squared minus 4L x plus 6L squared. And that's an L, you know, it looks bad, but it's an L. All right. So what do we do now? We have all of these units over here, right? So we should plug all of our units in. And when we plug all of our units in, what do we get W to equal? Got 24. We plug in E for the E. We plug in the units for the E, which would be newtons per meter squared. All right. I, meters to the fourth. Y, meters. And if I were to just move that over, I'm just going to move over. And I'm just going to move all that over, right? And I'm just going to say 24 newtons times meters to the fifth over meters squared. Right? And then that'll go away. When you're dividing exponents, what do? What does dividing exponents do?
Subtract.
Subtract. There you go. Thank you. So 5 minus 2 is 3. All right. So you got 24 Newton meters cubed, and that's all over. So just moving everything over, and then we're going to plug in for all of these guys down here, and all of these should be meters. So since I got x squared times that times that times that, let's just distribute. All right, so we got negative meter squared times positive meter squared will give you a negative meters to the fourth. And then we got minus, which ends up being a positive because I'm multiplying it times a negative, right? And then you got meter, meter. So you got negative turns to be a positive meter squared times 4 meters squared. So it'll be plus 4 meters to the fourth. All right. And then you have a positive times a negative turns out to be a negative. So you got minus 6. And you have L squared. So that's meter squared. And that's meter squared. So you got negative 6 meters to the 4th. All right. So when you add all of those up, what do you get? So when you add all these guys up down here, what do you get? You got negative meter to the 4th plus 4 meters to the 4th minus 6 meters to the 4th. And it ends up equaling what? Negative 3 meters to the 4th. Thanks, Chelsea. And then when you're dividing exponents, what do you get? Oh, sorry. It should be a Newton here too. Dividing exponents, you subtract. And 24 divided by 3 is 8. So our answer here would be negative 8 Newton meters. And that is your answer. So whenever you're working this problem, that's essentially what you're going to need to show me. You're going to show me the right. You're going to show me the formula you're starting with. You're going to show me what you're looking for, and then you're going to break down or isolate that variable, and then you're going to solve for that variable. Plug in all of your units, and then I'll need a final unit of measurement. So W is load distribution, which means the load distributed over a measure of length, and that's load distribution. All right, any questions? Now that you have problem 21 worked, you have, I believe 6 more. Yes, Mason.
At least for me, so I use Newton meters quite a bit, more as like a torque spec. So you're saying that this is like a negative, so this is like a load. How does that kind of work?
So for torque, it would be force times length. And then so for load distribution, it's load over a length. So if you have, so I hope everybody got that copy because I'm about to erase it. So you have a cantilever beam, right? Because that's what this is. And you have a load applied to this beam. And then what ends up happening to the beam, I'll draw it here. Beam ends up bending. There's some delta, or you can say X, some X. And so the question is, what is the load distribution over this length L?
Okay, I think
So,
I understand a little more.
Right. So he's basically asking, so W is basically, so this would not be W, right? This would be force. And so your load distribution, W, is how much force is distributed over that entire length.
Okay, cool. Yeah, I was just wondering how like the negative worked with that. So.
Yeah. So because the force is downward. Yep.
Cool.
So it was like, right, yeah, yeah. So I know you look and think about torque, and so you some torque being applied to a shaft or what have you. And it's like, wait, so how is it negative? Yeah, yeah, I get it. So yeah, it's just the direction. Because force is a vector, right? It has direction and a magnitude. And you'll learn that in physics. If you have physics, then you already know that force is a vector. And that negative is just showing the direction. All right, any other questions? All right, cool. So the other thing is that I want to share is significant digits. I know it's probably pretty elementary, but I always get students that miss this, and it's okay. So I'll just go over it. So significant digits are figures. Engineers make measurements and carry out calculations. So remember I was telling you last week or last class period about tolerances. And when you're making a hole in something, you always want to go to 3 significant digits. Why? Because you want a tighter tolerance, because you want to make sure the shaft fits into the hole or what have you. And you also want to make sure that it's not bigger than the hole, and you don't want tolerance stack up, that the shaft will never be bigger than the hole, right? And so we usually use 3 significant digits. All right. So if I were to show you this guy, 1785, 25.5, 1.85, and 0.00125 each have 3 significant digits. Y'all agree with that? Of course you do, right? Of course you do. So say I said 1500. How many significant digits is in that one? Some people may say 4. Some people may say 2. Right. But it's not clear. So you would say, because it could be 2, 3, or 4, you say it's undefined. Exactly. It needs a decimal to be clear, right? And seeing that you don't zeros, right? So you make it undefined, or you list 2, 3, or 4, and you say not clear. Also, if we recorded 1.5 times 10 to the third, or 15 times 10 to the 10th, then you have 2 significant digits. So this is just something to keep in mind when you're working your homework problems. All right. That was really it. And you already know when you're subtracting decimal places, you need to keep, the decimal or the units aligned. So like 152.47 minus 4 minus the 3, that's incorrect, right? You need to have your decimals aligned. It'll be 152.47 minus 3.9. I know a lot of this is arithmetic. You learn a lot of this in either Algebra 2 or grade school. Mostly Algebra 2. I know we did a lot of this in Algebra 2, but you should have learned it before then. But in either case, this is how you would work those problems. It's like simple errors that we make because we're rushing, because it's so simple math, right? And it's like, wait, why are we doing this in the college engineering course? Just because you need to know, you need to keep decimals in mind, especially when you're looking at tolerances and things of that nature. All right. Any questions? Good. That's pretty much it for lecture. Chemistry, yes, you will see it a lot in chemistry, definitely a lot, because when you're doing the balancing those reactions, so you'll see a lot of that. Yes, Lawson, you have a question?
Never mind, sir.
Right, chemistry was starting 2 years ago, absolutely. So that's why this is good practice, and so that's why I went over it to refresh your memory. All right. So if there are no other questions, let's look at this lab really quickly. Viscosity lab. And then I will turn you guys loose. Oh, wait. It got really big. All right, there we go. Nope, that ain't what we want. There we go. All right, viscosity lab. This lab is pretty fun. Well, reasonably fun. How to calculate flow rate, cross-sectional area, and velocity. All right. So there's your viscosity. Sorry. There's your viscosity equation. It'll be gravity, 2 times the gravity, radius of a sphere, squared. And that'll be rho fluid minus rho sphere. And remember rho, density. And you're dividing it by your velocity. And it looks like 9 times the velocity. So let's get to the meat of this. What are we looking for? So what you're going to do, you're going to have a bottle, the cross-sectional area of the bottle. So I would suggest getting some plastic bottle. If you have water bottles around your house, if you don't, go buy a couple because you're going to need a couple different ones. All right. And then you're going to basically flow a fluid through it. Right. And then here's the equation for that. You got rho times V dot. V dot is volumetric flow rate. And how you solve for that, which is pretty cool. So you have the density of your fluid, which you're going to use water, right? And then the area, the cross-sectional area of the bottle. So you just measure the diameter, and then basically it is pi r squared. Okay. And then your V is your viscosity. And that will that will basically help you to see what M dot is. It'll help you solve for M dot. So then this is what your procedure. You're going to have water, canola oil, or motor oil. If you don't have motor oil, you can do water, some type of a vegetable oil, and just some thicker fluid, something a little thicker than oil. I wouldn't use peanut butter, because it ain't gonna really flow too well. Maybe ketchup. Ketchup probably won't flow as well either, but that's cool. You want something that it's not gonna flow very well. Honey, there you go. Honey, that's a good one. Or syrup, that's another good one. So a lot of you may not have motor oil around the house, so use syrup or honey, and those are perfect. I love it. Thanks, guys. And so you're gonna use that. You're gonna basically flow this through the bottle, and you're gonna time it. You're gonna see how fast it flows. And that's pretty much it. Real simple, easy. You're gonna make a graph basically of the time. Either you're filling it or flowing through it. All right. And then you're gonna just show the time for each. Quantity should be the same because you're using this. You can get 3 different bottles, right? Because you don't want to mix them. So, and you can just chart it as such. And you're just calculating the mass flow rate. Yeah. Sorry, what was the question again? Cassandra, let me look. How many liquids do we need? Just those 3. Yes, Mason.
Are we doing this with the groups too, or is this individual?
No, yeah. This is with your group. So every lab will be with your group. So you can pick one. Each person can do a fluid, a different type of fluid, and then you all can just collect your data. You all can do it together. Here again, Texas. Hey, there's no more coronavirus in Texas, so you can meet up, or you can do it virtually, however you choose. So, and I think next fall we're going to be doing a lot of more in-class, actually in-class sessions. So, who would have thunk it? But anyways, yeah. So pretty simple lab. You have the equation for calculating mass flow rate, but for the most part, you are just timing your fluid. You have your volume because of the volume of the bottle. So, any questions? Other questions? Nope. All right, cool, good deal. So it's about 14 of you guys here. We have 18 students, so 4 people aren't here. Do you guys want to break up into labs, or do you want to break up on your own? Just up to you. All right, well. All right, cool. So, yeah, you could go, Sahil. I think just let me chat with you for a minute. But everybody else, you guys could break up into groups, however you choose. Uh, who was in who was Jacob in your group? Sahil? I can't remember. Was it you and Jacob? Okay. All right. So yeah, Sahil, just stay with me. Everybody else, uh you're free to go.